This is lesson 6.3, scatter plots, exponential and linear situations. You will need a graphing calculator for this lesson. Okay, to begin, we've got a question where you are going to graph the data on the coordinate plane. And so we're talking about pairs of bald eagles. And so remember that since we're talking about a situation, we need to label our x and y axis. So this is going to be the number of years, and that's years since 1960. So let's put that. And then on the y-axis, it's the number of pairs of bald eagles. So if we write 1, then that means there's one pair. And so that's what we're going to put there. So pairs of bald eagles. Okay, so go ahead and pause the video so you can make your scatter plot, and then we'll come back and talk about what we see. Okay, I do have my scatter plot done, and you should too. And so if you haven't answered the questions down below, then I want you to go ahead and pause the video again and answer those questions first, and then come back and let's compare answers. Okay, for number 2, it said to sketch the line of best fit, and it said don't use a ruler. Now, why do you think I would ask you to not use a ruler? Let's look at this. If we were going to draw a straight line, if it's going to fit most of the data, it'd have to be something like that, but it totally misses the first data and the last data. And if I was to get the first data, we totally miss the rest of it. And if I get the last data, we miss most of it. And so it's really hard to get a line that really does fit the data. And so if you look and think about what other things that we know about, think about an exponential curve. So what if we did something like this? That's going to fit the data a lot better. And so your curve might not be exactly the same as my curve, but it's the same idea, and you're hitting a lot of those points or kind of going alongside a lot of them. So something like that. And so that would fit our data better than a line would. And so the thing that we notice is different is it's going to be more exponential in nature. And so sometimes data is exponential instead of linear. And so if it's exponential, doing a linear equation doesn't fit that. And so we want to be aware of that. The general form of an exponential equation, remember, is y equals a times b to the x power. And remember that this is our initial value, or our y-intercept. And this right here is our rate. And so remember, if it's greater than 1, it's growth. And if it's less than 1, it's decay. And it's never going to be equal to 1. So if I look at what this is, if I was going to come up with the equation, I would be looking at something like, I don't know, maybe 200. And then it's increasing a lot as far as trying to figure out how much. It goes from, I don't know, 200, and then each year it's increasing not 100%, but it's, increasing by more than 1, so 1 plus something to the x power. So we'd have to look and see, but how do you figure out exactly what that equation is going to be? So that's what we're going to learn about today. Okay, so we are going to learn today how to use our calculator to find this, and it's also a good idea because Desmos is on the internet. And it's a good idea, it's not very hard to learn how to use Desmos to do this. And so those are the steps if you want to do that. I would like you to know how to do it on a calculator because on the test that's what we'll have. But Desmos is a good option as well. So I'm going to show you how to enter this data into your calculator. It's very much the same as what we did for a line of best fit. So you're going to start by resetting your calculator, turn diagnostic on. Again, that's so you get your R. Stat plots on. And so all the same steps to begin with. Now for the window, use the graph that we just saw to set your window. So you want your window on the X, you want it to go from 0 to 60 and by a scale of 5. And on the Y, you want it to go from 0 to 10,000 and you want it to go as a scale of 500. Okay, so when you go and set up all that stuff, that's what you're going to do. So pause the video and go through all of those steps, and then we'll go through entering the data and finding how to find the equation for the data. So I reset my calculator, I turned diagnostic on, I went to stat and I entered all of my data on the bald eagle, so there's all my data. I went to window and I changed my window to match what the graph is on the paper, so it will look the same. I made sure that my stat plots were on. Okay, so it's got stat plots on. So once I've done all of those things, then I'm going to do a graph and it will show me the scatter plot. And so I can see the scatter plot. Now it's a little bit more wide than it is tall. On the paper it's actually taller than it is wide, but that's just a screen thing, so that's okay. But I can still see how it's not, like this part of it looks like it might be linear, but there's too much out there and too much up here that's not linear, so I can see that it's more exponential. And so one thing that doing the scatter plot on the graph or on the calculator will tell you quickly is you can kind of get an idea of if it looks more linear or exponential. So what I'm going to do to get my equation, I'm going to go to Stat and Calc. Now, if we do what we did last time, we go to linear regression, that's going to find the equation of a line of best fit. So let's actually do that first. So if I go down to linear regression and I get a line of best fit, that's what you should get. So go ahead and just see if you get that. Now, one thing I want you to notice here, it's increasing by 200 every year. It had a y-intercept at negative 2,646, so that seems a little strange. But remember that it's just a line of best fit. It's not actually, exactly factual. So that is okay. It sometimes happens like that. Notice the correlation coefficient is 0.906. So that's pretty strong, but we've seen stronger correlations. And so that's the correlation of a line. So how well does the line fit the data? So let's actually put that in and see how it matches up. So I'm going to type in this equation. So 213 x minus 2646. So I'm going to come over to my y equals menu, and I'm going to type in 213x minus 2636, I think it was. I better go back and check and make sure that that's what it said. Negative 2646. So I need to change that. Okay, and then if I graph it, it's going to put that line next to my data. So we kind of see the same thing that we did if we were trying with a ruler on that problem, that it doesn't really fit. So let's go to Stat and Calc. And then what we're going to do is we're going to not do linear regression, but if you keep on going down to 0, it says exponential regression, and that's the one we want if it's exponential. So I'm going to choose that one. So exponential regression, you're going to go through the same thing, like it's going to make sure we're using the right list and everything. We're going to calculate it. Notice how it says y equals a times b to the x, so we know that this is an exponential equation. It gives me a is 315. That means in year 0 we had 315 pairs of bald eagles. That seems really reasonable, okay? And then the rate is 1.077. So if you think about what percent that is, that means that it was 1 plus 0.077, or it grew by 7.7%. Okay, so that seems reasonable. But look at my correlation coefficient. Look how much stronger that is. So the other one was 0.90. This is 0.987. That's much, much stronger. So this should fit a lot better. So if I go and put this curve in, let's do that one and compare it. So 315, I'm just going to round to the nearest whole on that one. With my rate, I don't want to round to the nearest whole, because if I go 1, then that's just going to keep everything the same, and it's going to be a horizontal line. So I'm going to do 1.078. Okay, so I'm going to go and put that in. So 315, I'm going to come down here to y sub 2, and I'm going to say 315, and then times 1.078, and that is rounded a little bit, and then to the power of x. And now when I graph that, I'm going to see how well that compares to my data, and that looks like that fits a lot better. Look at how well that fits on my data, and that's why my correlation coefficient is so much stronger on that one. And so if you were trying to decide, you could do both ways and see which one works. So an interesting little thing, if you go back on your homework last time with the COVID-19 data, and if you try that and see which one fits better, you can actually try a linear function and an exponential function. And it might be a little surprising to see which one is actually better. I guess it was actually on the lesson, not the homework. But if you go and you see, like we did linear on that, because that's all we knew at the time, and you might think because of what you've heard, like, oh, it would be exponential. And so you can actually check and see. And so go and try that and just see if you're surprised. Now, of course, if we had more data, like if we had December's data and January's and like the next few months, like as, you know, if cases were still continuing to increase, I know that in December they did, but we might see something slightly different. But just based on that data, are you surprised? So just a thought question for you there. Okay, so I'm just going to go in and put my equation that I had on my calculator in here, and I'm going to be doing my exponential one. Now, I didn't tell you specifically where to round, and so on a test or on a quiz or something, I will tell you where to round. So generally speaking, it's probably fine to round that one to the nearest whole, but this one you definitely want to go at least 2, but maybe 3 decimal places, because you want to be as accurate as possible. And where you're getting that decimal place, you know, anything beyond 1 is the growth, and so you want to make sure you get all of that in there. Okay, so now what is the correlation coefficient? We got that, and it was 0.98, and so we knew that it was pretty strong. Okay, actually 0.987. So with correlation coefficients, you probably, like, 2 is the absolute minimum decimal places you want to go. 3 would probably be better. So the correlation there, we're going to say strong and positive. So don't just say strong and don't just say positive. Say strong, positive when you're asked to describe the correlation. Okay, write a sentence, explain what the initial value means. So what does the 315 mean? So think about, it's our initial value, it's at the beginning. So in this context of the problem, if we go back and look at what this was talking about, year 0 right there, that was since 1960, so that was at 1960. So I would say in 1960 there were 315 pairs of bald eagles. And then write a sentence, explain what B represents. So the growth, it grew, or it grows, at 7.78% per year. And so remember, it's not 1.07, that's the rate, but the amount that it grows. So you could also say the rate is 0.078 per year. I think I got too many 7s in there. See, 7.777, that's what it would be. Nope, 6. Because you had 1.0776. So if I'm going to go percents, it's going to be 7.76. So if I say the rate is 1.07, I could do 8. That actually wouldn't be wrong if I wanted to round to this place value. The 6 would tell me to make that go up to an 8. So you could do that, or you could say 7.6. Okay, those would all be right. And so it just depends on where I tell you to round. Okay, for the next part, I'm going to pause the video and you are going to get your calculator. You don't really need to do the scatter plot on paper, but I have the scatter plot there because I want you to see, like, okay, here's how we're going to do our window on our calculator. So you don't need to put the scatter plot on paper, but I want you to enter the data into your calculator, make a scatter plot on your calculator so that it shows you the points, and you can decide, does it look linear or exponential? And then you're going to you don't need to sketch the curve, I guess. Just look at your calculator and just decide what that is, but maybe say which one it is right there. And then using your graphing calculator, I want you to answer these questions. Then you're going to turn the video back on and we'll go over what the correct answers are. Okay, instead of doing the graph on paper, I have taken a picture of what my calculator looks like. And so down here, this is the year since 1900. So this is 1900, and then we've got 1910, 1920, 1930, and this all comes from census information. So this is actually year 2010 because it's 100 years past. Now notice at the bottom of your graph, it starts actually at 200. So actually my y-intercept is a little bit above 200. And it doesn't mean 200 people, it's 200,000 people in Utah. And so then it increases, and so at the top when it's like 2,800, that doesn't mean 2,800 people live in Utah, it means 2,800,000, and so that means 2,800,000, so that's what that means. Okay, so that's what my graph looks like, and then if you go and you have your calculator figure out the rest of it, the equation that you should have gotten, and it says round a to the nearest whole number and b to the nearest thousandth, so that's 3 place values. So it's going to be y is equal to 276 and 1.021 to the x power. So that's the correct rounding for all of that. So go and check and make sure you've got those numbers. If you're not getting those numbers, then my question is, did you enter your data correctly? Because if you get one number wrong, those numbers will be off. So you need to be very, very careful when you do that. Okay, the correlation coefficient to the nearest thousandth is 0. You don't really have to write the 0, but I like to so that the decimal shows up. And then it's 0.9951. So 99, the 1 will have us keep the 5. You never, never want to round your correlation coefficient to 1, because then it seems like it's perfect. And we know that it's not perfect. Okay, describe the correlation. That is very strong, positive. So it's almost as strong as you can get. Whoops, I couldn't spell. Positive. Write a sentence explaining what the initial value represents. So what does 276 mean? Okay, so 276, that's at the beginning. So in 1900, it means according to our equation, there were 276,000 people in Utah. Now the question that people have often is they'll look at this and they'll say, but wait, it says up here that in 1900 we have 277,000 people. So how come this one only says 276? Remember that this is the curve that best fits the data. So that's going to maybe be a little bit lower or a little bit higher because it has to fit all of the data. So that's a very common thing. So don't be alarmed by that. Okay, write a sentence explain what the growth or decay factor represents. Well, obviously this is a growth factor because it's bigger than 1. So since you have 1.021, how much did it grow? So change it to a percent. So it's 1 plus 0.021. And so that means 1 plus, and then that's 2.1%. So the population in Utah grows, according to this, at 2.1% per year. Okay, now we soon will have 2020 data, 2020 data from the census, and so it'll be interesting to see, like, do we continue that, or did it grow faster, like more than 2.1%, or is it lower? And so that's how you tell if a state is growing or not. Okay, the last part of this is we're going to do another table, and this is just for practice. Again, you do not need to do the actual table on the paper, but I've got the scale there so you know like how to set up your scale on your calculator so you make that match. This is radioactive data, so we're going to have how many seconds have passed and how many grams do we have. So if you look at the grams, what's happening, okay? And then you're going to again answer the questions and then just come back and we're just going to compare and make sure that you have the right thing. Okay, I've entered my data into the calculator, and this is what my scatter plot looks like. I want you to notice that right here, and this is just something to watch, even though it says 0, 1, 2, it says 16, 17, 18, so this has to be 15. And so just be aware that sometimes the x and y axis are not going to show the origin. So just be aware, and that's just because like it's too far down, and so we're not worrying about that part. It's kind of like we're actually just, if we have the origin down here, we're actually just showing this window of it. So we're starting higher, and so that's just so that we can see what's in the window. Okay, so if I look at my graph, along here, this right here, the x-axis, that's how many seconds have happened. And this right here is how many grams I have left of my substance. And so we're starting up here, and it's going down. Okay, this is radioactive, this is decay. And so hopefully all of your information shows that. Okay, now as far as sketching the curve that best fits your data, can you see what that would be? And so if you had something like that, could you do that? Since I'm not making you do it on the paper, just make sure you feel like you're comfortable with that. If you feel like you want to do it on the paper to practice, then that's fine too. Okay, the equation that best fits your curve, you're going to go to your calc and you're going to go to exponential regression. Make sure you've got your tables right. Again, if you've typed anything wrong, it's going to be off. Your equation that you should get is y equals, and then it says about rounding, it says round a to the nearest whole number. So it says 32.6, so I'm going to go 33. And then my exponential, it's decay, and so I expect my number to be less than 1, which my number is 0.9675, so that's good because it's less than 1. So I'm going to say, because it says to the nearest thousandth, so 0.968, because the 5 will make the 7 go to an 8. To the x power. Don't forget to the x power, because that's how you get an exponential. The correlation coefficient, notice that it's negative. Now, something that people miss sometimes is they don't see that it's negative because they see the equal sign and then they just kind of skip past the negative. So make sure you notice it's negative. If it's decay, it would have to be negative. And then to the nearest hundredth is 0.94. Okay, the correlation, it's strong, but it is negative. Okay, so just because it's negative, it's still fitting very well. Okay, write a sentence explaining what the initial value represents. So according to this equation, it means that at the beginning, we're beginning with 33 grams. So begin with 33 grams. Now, if you look back at your table, that's not what we began with. We began with more than 39.8. However, in order to fit all of the data, the graph that we're doing is going to show that we're starting lower just so that it fits. So it's not going to fit perfectly, and that's why things are a little bit off. That's okay. But that's what that number means. Now, as far as the decay factor, the 0.968, that means that it is decaying, okay, because it's less than 1. And remember that it's 1 minus whatever the rate is. And so you can find the difference. You can say, what's 1 minus 0.968? And you get 0.032. So it's decaying by a 3.2% per second. Okay? Or you can say, an alternative to that, you can say each second you still have 96.8% of the substance. Okay, so there's two ways you can look at that. So it does say the decay factor, and so that's the 0.968, and so this would be a great answer. However, you still are using the decay factor to tell me that you're decreasing by 3.2%. Okay, you should now be ready to complete your assignment on scatter plots and use your calculator, and also be ready for your test.